This question is from GATE Mechanical Engineering of 2014. This is question number 47 of set 1. The question is, in an air standard Otto cycle, air is supplied at 0.1 megapascal and 308 Kelvin. The ratio of specific heats gamma and specific gas constant R of the air are 1.4 and 288.8 joule per kilogram Kelvin respectively. If the compression ratio is 8 and the maximum temperature in the cycle is 2660 Kelvin, the heat in kilojoule per kilogram supplied to the engine is. That means the specific heat we need to find out in this problem. So let's start with the diagram of Otto cycle. So these are the PV and TS diagram of air standard Otto cycle. Process 1 to 2 is isentropic process, that means delta S, change in entropy is 0. Similarly 3 to 4 is also isentropic process, delta S is 0. 2 to 3 heat is added to the system, which is a constant volume process, so Q in, and 4 to 1 heat is getting out of the system, Q out. Okay, so this is how the cycle operates. 4 to 1 is also constant volume cycle, so delta V is equal to 0. Here also delta V is equal to 0. Similarly in the TS diagram, so here delta S is equal to 0, delta V is equal to 0, delta V is equal to 0, here delta S is equal to 0. So 1 to 2 is isentropic compression and 3 to 4 is isentropic expansion process. Now in the problem it is given that the compression ratio, let's say R, let's write small r, compression ratio is 8 and the maximum temperature, that means T3, is 2660 Kelvin. Okay, these two information as well as the value of gamma and capital R, that is the gas constant, specific gas constant is also given. Now let's use these values, and from this diagram, from this Otto cycle, we can write process 1 to 2 and 3 to 4 are isentropic processes. We have already established it here. Therefore, it will follow the isentropic relation. We can write T2 by T1 should be equal to V1 by V2 to the power of gamma minus 1. So from here, T2 will be equal to T1 times V1 upon V2 to the power of gamma minus 1. Now, the value of T1 is 308 Kelvin. Okay, this information is also given. See, air is supplied at 0.1 megapascal and 308 Kelvin. That means P1 and T1 both are given. Okay, so T2 we can find out. T2 will be equal to T1, that is 308 multiplied by V1 upon V2, that is the compression ratio. So it is 8 to the power of 1.4 minus 1. So this is gamma, don't confuse with it R. Okay, small r, that compression ratio. Let me write it here. V1 upon V2 is equal to R. So this value from here T2 will get is 707.6 Kelvin. Okay, now T2 we have got. So process 2 to 3 is isochoric process, right? 2 to 3 is isochoric. That means change in volume will be 0. Okay, we can write Cp upon Cv is equal to gamma, which is 1.4. we know this, and also Cp minus Cv is the gas constant R. So in the problem it is given 0.288 kilojoule per kilo. Let's write kilojoule per kilogram Kelvin. Okay, now we need to find Cv value. So if we substitute these two, we'll get Cv is equal to 0.722 kilojoule per kilogram Kelvin. Okay, now we can find heat input. So Q in will be equal to, let's write heat added to the cycle or to the system is equal to Cv T3 minus T2, which is equal to 0.722 times T3 is given 2660 minus T2 we have already found here 707 0.6. Okay, so from here Q in, heat added to the system will be 1409.63 kilojoule per kilogram. Okay, now let's fill in the blank. So the heat supplied in kilojoule per kilogram is 1409.63. For more information, you can refer to the NPTEL course lecture number 59, Auto Cycle, on Concepts of Thermodynamics by Professor Suman Chakraborty of the Department of Mechanical Engineering at IIT Kharagpur.